As I mentioned, 2/3 of the second semester of freshman chemistry are devoted to a look at something called equilibrium. And in fact, they divide so that some of what we look at is physical equilibria. That's what you'll find in the first several lectures. And then we spend a great deal of time looking at chemical equilibria, and in particular within chemical equilibria at the idea of water chemistry. So it's important as we begin today's lecture that we understand the foundational idea behind what it is that explains what physical equilibrium is. Remember that the Gibbs free energy equation, which you can derive from the second law of thermodynamics, says that delta G is equal to delta H minus T delta S. And we know that there's this crossover point between a reaction happening and a reaction not happening, and that crossover point is when delta G is equal to 0. Now, if I rearrange this, I can get all sorts of interesting information out of this that will allow me to do lots of calculations concerning how to find a boiling point or an entropy change at a phase transition, things like that. But what I'm particularly interested in here is what it means for delta G to be equal to 0. And I drew a picture last semester, which I'll put back up here for you now, in which what we do is we evaluate this thing called energy on this energy scale here for some kind of process. And I don't really care what the process is, whether it's a chemical process, whether it's a physical process. Let's choose a chemical process, for example, right now, where I have a bunch of A. Suppose I have 100 A, and I have no B. And this is a reaction in which I'm watching A going to form B. What will happen is that this reaction will move to the right. And as it moves to the right, I'll have less and less A, and I'll have more and more B. You actually have this driving force that moves me toward the place where I have less A and more B. The point is, it doesn't go to completion. Rarely do reactions get to the point where essentially all of A has gone away and only B remains. Instead, it's going to fall to the bottom of this hill to a point where there is a certain amount of A and a certain amount of B. Maybe that amount of A will be something like 33, and the amount of B will be 67. Delta G is a measure of just how big this fall is going to be, down to the point where I have 67B and 33A. Obviously, if I start with all A and no B, it's going to be a big fall. But if I'm somewhere down here, maybe at the point here where it's 70A and 30B, the driving force for this reaction isn't as great. But you can see I'm falling down this hill with a constant change in the amount of free energy in the system, free energy change in the system, until I get to the point where this is the result that's left. It's also interesting to note that I can go back in the other direction. I could start with 100B and 0A. There's nothing that stops me from having this reaction be the one I'm watching. And so in this particular case, the driving force is in the reverse direction, to the point where, and this is what's key, I get to where I have 67B and 33A. You see, it doesn't matter whether or not I am starting with all A or whether I'm starting with all B. When it's all said and done, I'm going to get to this point where the ratio of the B to the A is going to be equal to the same value. This is actually a value we call the equilibrium constant. And this equilibrium constant will pop up over and over again no matter what kind of physical or chemical process we're looking at. It is the value for the ratio for the concentrations of the things that we're looking at the bottom of this free energy hill. So what we do to deal with this is to appreciate that because a reaction can go in both directions, it's no longer fair to talk about a reaction as simply going to the right. Instead, we write it this way, appreciating that you can start out with any combination of A or B, and what they're going to do is, whether it's all A or all B or anything in between, the delta G of reaction, the free energy of reaction, is going to result in getting yourself to the point where that ratio for K, in this particular case, the ratio of B to A being about 2, is going to be achieved. And once that is achieved, you are at equilibrium. It's this value right here, at equilibrium, which is what we measure throughout 2/3 of the second semester of the course.